let's go ahead and get rolling. Welcome to today's webinar. Today we will be discussing geologic structure modeling for geotechnical applications. We've got our panel of experts here who I will introduce formally in just a moment. But before I do that, I'm going to give you a little bit of background on the Geotechnical Center of Excellence, also known as the GCE. We are putting on this webinar for you today. So we are part of the School of Mining and Mineral Resources here at the University of Arizona in Tucson. We are an industry-funded group, and we are member-led, and we are an interdisciplinary center. We bring a lot of different disciplines together to conduct collaborative geotechnical research, as well as education, professional development education, like the webinar that you're tuned into today. We also pride ourselves on bridging gaps within and between academia, industry, and other fields of study. So as I mentioned, we are member funded and member led. Here is a list of our member companies, and without them, none of this would be possible. So a huge shout out to them. If you're watching today and you would like to become a member, we'd love to start that conversation. You can contact us at gce@arizona.edu or find us on LinkedIn. If you know any of us personally, you can go ahead and just reach out. We'd love to start that conversation with you. So this webinar is based on our Structural Geology for Geotechnical Professionals course. This is a professional development course. It is currently ongoing. It started in August. It's a 12-week asynchronous online course. So all of the modules have been released, but the course will remain open until August of 2025. But and if you'd like to learn more about that, you can follow this QR code. We will be re-releasing the course in June of 2025 as well, where you could follow along with the course releases. I should also mention that we have 4 additional courses, and we've just released our newest course last week, which is the fundamentals of open pit slope design. And one of my trusty co-hosts could put a link to some of our courses, more information, that'd be great in the chat. Thank you, Julia. So this course was also underwritten and created in collaboration with the Large Open Pit Project, the LOP. So a huge shout out to them. And as always, a big thanks to our panelists joining us today, our advisors, and our other collaborators. It's a huge endeavor putting these together, so we really appreciate everyone's time and effort. So just a couple quick housekeeping notes before we get started. If you're joining us today, you are muted and your video is off, so no need to worry about that. If you'd like to ask a question, please use the Q&A function at the bottom of your Zoom control panel or top, wherever it is. It looks like this little button shown here. It looks similar to the chat function, which we encourage you to use both. But if you have a specific question for somebody, please use the Q&A. It helps us keep everything in line. But go ahead and feel free to use the chat to say hello or to have any other comments or suggestions. You can also answer, or you can post questions anonymously if you choose, and you can also vote for them. You can give them a little thumbs up. So we encourage you to do that, kind of high grades the questions, so we can sort through those. This is also a recorded webinar. We will post it to our structure course page, as well as our YouTube page, which we'll post a link to in the chat. And just a quick disclaimer, we want to note that this webinar is really intended for educational purposes only. If you're having issues at your site or with your work, we encourage you to seek professional advice. So now a couple of introductions. I will be your moderator today. My name is James McNabb. I'm a senior research and development engineer here at the GCE. And I've got 3 co-hosts joining me today. First is Julia Potter. She's the director of the GCE. Good morning, Julia.
Morning, James, and good morning, everyone. Thanks for being here today.
Next, we have Benjamin Meyer. He is a research and development software engineer with the GCE. Good morning, Benjamin.
Good morning, everyone. Thank you for coming today.
Next, we have Christian Ortman. He's a computing sciences researcher with the GCE. Hello, Christian.
Hey, James. Good morning, everyone. Thanks for joining us today.
A little quiet. That's okay. So my co-host will be working hard in the background, fielding your questions and making sure everything is running properly. So thanks for being here, guys. Okay, now let's get into our expert panel. First, we have Neil Seifert. He's a project technical specialist with Tech Resources Limited. Hello, Neil.
Hey, James. Good morning.
Good morning. Next, we have Luca Zorsi. He's a Principal Geoscience Specialist with WSP Canada. Good morning, Luca.
Good morning, good afternoon, good evening to everyone.
Next, we have Ian Besson. He's a Principal Member with Tech Geological Consulting. And good evening, Ian.
Hi, everyone. Good to be here.
Next, we have Graham Banks. He's a Senior Principal Geoscientist with Route to Reserves and Geothermal Energy Advisors. Hello, Graham.
Hi, everybody.
Next, we have Finley Fraser. He's a Principal Consultant with SRK Consulting. Hi, Finley.
Good morning, everyone.
Next, we have Wayne Barnett. He's a Principal Structural Geologist with SRK Consulting. Hello, Wayne.
Hi, everybody. Happy to be here.
Then we have Jeff Owen. He's the Manager of Structural Geology of Mining Operations Advanced Project Exploration with Teck Resources Limited. Hello, Jeff.
Hi there, everyone.
Okay, that is our expert panel. And we're going to get started today with a kickoff topic. It's sort of just a broad overview question. So let's go ahead and get into that. So there are many types of geologic models utilized in mining that have common elements but are used for very different purposes. For example, hydrogeologic or resource models. What are the key elements that comprise structural models for geotechnical applications, and how do they differ from other models? And I'm going to go ahead and assign this to Wayne. I think you gave a really good presentation in the structure course, so if you could maybe get us started on this, we'd appreciate that.
Yeah, sure. Thanks. Good morning. Look, I think the main thing is what do we need to understand to support the geotechnical models? And to me, it always comes back to the PPC, properties, pattern, and continuity. So understanding the continuity of the structures and the properties of those structures, and understanding the overall pattern that forms the basis of what you're going to use to build that model, and once you've got a model like that, then you can start to use that within geotechnical slope stability analyses. It's simple as that. Someone can add.
Very succinct. All right. Anybody else want to jump on that?
I think I'd like to add just a little more detail from the perspective of just building out a model, something that really is very different visually when you step into looking at a model that is set up for geotech rather than one that resource domains, is you're going to see a much higher density of structures in that model. So we're going to be looking to add a lot more detail around smaller structures, discontinuous structures, structures that aren't just domain boundaries are going to find their way into this model as well. So all of those elements that Wayne described with properties, pattern, and continuity, that's going to be reflected in a 3D model with a lot of much smaller faults that don't necessarily form major domain boundaries individually.
Great. Thank you, Finley.
Yeah, and just to add what Finlay just said and Wayne, it's also it entails a different approach even when it comes down to data collection or data analysis and review. So as Finlay was saying, it's a different types and family of structures that needs to be taken into consideration. And for other models, let's say a resource model, tend to be sometimes very much overlooked.
Very good.
Yeah, I'll just toss in a comment as well. I think, yeah, in terms of key elements, I think that a lot of the elements that we use for developing our structural models are actually can be used for a bunch of different types of models, right? So if we start, I think us as structural geologists, we have the opportunity to take a very holistic approach. So we're going to want to use assay information, geochemical information, geomechanical information, geology. So we have this opportunity to be able to incorporate all these various types of data, and then to use those to interpret what is actually a fit for purpose model for whatever that stakeholder is. And as the teams have alluded to, I think, a great point, like for a geotechnical application, the PPC, looking at shorter persistence and structures, it's almost like I feel like for majority of these models, we can still use a very holistic approach, but there's almost a bit of a prioritization on which data we need for certain stakeholders.
Yeah, very good. Any other thoughts on this? Graham, I see you've unmuted.
Yeah, just one comment to follow on from
Yeah.
what Jeff just said there about the communication and the stakeholder. Just always make sure you're in regular communication with the client. What do they really need and what's going to make a material impact on either their balance sheet or their project or their next decision. And always make sure that you focus the right amount of time on what's going to make a material impact rather than what's not going to make a material impact. We look at the things that we like to look at rather than what's going to have the biggest, what's going to enable a decision maker to make their decision easier.
Yep, great point.
Really important.
I just want to maybe reiterate a comment that was made in one of the previous Q&A sessions, is that when you're on a mine, if you're working for a mine or you're a consultant, you tend to get channeled into a particular aspect of a model. So your contract, for instance, will be with the geotechs or with MRM or with hydrology. It's quite rare to have a kind of a, one ring to rule them in the darkness behind them, so to speak. It's not that often never happens. We're working for Endeavour at the moment where they do want these kind of models that can be used by every department. But normally you get channeled into a particular silo, if you like, and that may strongly influence the emphasis that you place on a particular data set. And in fact, if you're not careful, you can actually surprise the people on the mine and, arrive at their desk asking for their data and they have no idea who you are. So unfortunately, the practicalities of it tend to lean towards being channeled into a particular model, but you really do need to try and make your model as fully informed as possible and be true to that sort of shared earth philosophy where, all your data sets share the same 3D volume, really. So they should express themselves in your model. And it is an extra effort to go to the office next door if you're working there, or if you're a consultant, to go and knock on someone's door to ask for their data. But you do need to do it. Even if you are only building a geotech model or an MRM model or a hydrological model, it's still worth doing that, as Jeff has said.
Yeah, I love that comment, Ian, and I've been thinking that'll be a good discussion here today. So I'm glad you brought that up and explained it. I find a lot of clients think that they have to focus just on the structure or just on the hydro as a model, and I totally agree with you. You can build a model with all those components, all the necessary geotechnical components included in the model. So I think that's great point.
Okay, very good. I think that was a really, really good kickoff discussion there. Following on this last point here, let's see if I can find this question real quick. This is in reference to what you guys were just talking about, combining models. Are there efforts to use AI, artificial intelligence, to combine multiple model types for more robust interpretations or design capabilities? I think this is just alluding to the fact that combining models can be quite complex. So using AI or machine learning to address that complexity. See a couple people unmuting.
There's a bit of a pause here, so I'll maybe get us started.
Please do.
Look, I think in terms of what the AI tools are doing, I don't think we really understand yet. I think there's a lot of people on the call have probably used machine learning in one capacity or another. We've used it a little bit in our group here, but I don't think we really are able to see the full vista of opportunities here between the different tools, the open source ones, the off-the-shelf ones, and how they're going to change it. I think where I'm seeing machine learning really making a difference is in being able to create large comparable data sets from things like core photos, being able to create one data set where we can actually compare all the values across a whole deposit without worrying about different generations of data or logging, for example. I haven't yet really dove into tools that are going to start cross-referencing different data types, but I'm sure others have. I think what I see at the moment, my experience has been that machine learning is generating really interesting capabilities on the data generation side. I don't know how many I haven't seen, but I'm interested to hear others' experience on whether that's different on the analysis and the model generation side.
Yeah, maybe I can add to that, Finley. I think from our perspective, we've been using AI tools to make the data side and the input data to our structural models more effective and efficient. Ways of, making it more efficient to collect the data, to interpret that original data set. We haven't particularly been where we haven't used AI to combine different structural model types. I know there's advances in the space of rapid modeling, like domain MCF, and using AI tools to create rapid geologic models. I mean, from my perspective, I think there's a bit of an issue there because it's really hard to bring structural interpretations into these rapid modeling tools. And I think whatever path we go down with AI, we can't lose that connection to that structural interpretation. I think that's really key. I think AI is going to really help us make the input data more effective, efficient, and accurate. But I think keeping that structural geologist tied to the interpretation is key.
Very good point. Luca, I see your hand is raised.
Oh yeah, just to to touch on what Neil just added, it's true. A lot of the tools that are available right now, they tend more to work towards the domain aspect, so a domain model rather than, let's say, a structural model, and they tend to generate a model. So it's not really a stochastic approach in which you can test multiple models and get like a distribution of, the probability of, let's say, on how realistic that model could be. But Neil brought up the good point is that sometimes, depending on the stage of a project and the availability of the type of data sets, you don't even have simply multiple 3D models options, like how you connect data from a drill or a mapping data. But you can also come up with different conceptual understanding of the areas, depending again on the stage of the project, that they're all equally plausible given the data, the knowledge available at that specific site. So it's there is more to that, because we need to combine, as Neil was saying, the interpretation side of thing, so the conceptualization of the model, and then the realization of the model itself, like the 3D model, or the multiple realization given the data, given a specific geological interpretation.
Yeah, great. Ian, I see you've unmuted.
Yeah, thanks, James. My concern would really.
Oops.
You muted, James.
Sorry,
Yeah.
I beg your pardon. My first concern would be for me to understand how AI works with the data, and secondly, to communicate that to the client. I mean, I could easily imagine a scenario where we're standing in a room and I'm trying to defend an AI model to a mining engineer or geotechnical engineer or to a technical services manager, and it makes the hair on the back of my neck, stand up straight. So, could you do a back analysis on an AI model, for instance? How would that work? So I can see how AI machine learning is used in regional exploration projects. I mean, it's maybe a step beyond mineral systems analysis or layer driven or data driven. That's fine, but I don't quite yet see how it's going to work in the 3D geotechnical stroke mining world. I'm sure that time will come. But right now, for me, the main concern would be trying to explain and defend that model. And thirdly, once you leave the room and you go back to your office or you fly away, that model is now on their server. You may have someone who opens it in a year or three's time. Do they understand it? Do they think it's the gospel that they can then hang their hats on? You know what I mean? So you've created something and you've left it there. These are all serious questions we need to really think about before we go too far down this road. Anyway, that's all I'll say for that. Thanks.
Yeah, great point.
Well, on what Ian was saying is that I would just add, I see this as an opportunity, exploring AI capabilities. I see these as opportunities to actually back up a little bit more what we present to a client, in the sense that very often we find ourselves deciding for a model. That is the model that we need to give to a client or to our colleagues, whether it's a hydrogeology or geotech or resource. And it's a model out of 2 or 3 or 4 possibility. That fault could go that way, but it could actually bend that way, or the interconnection between those structures could be X, Y, or Z. But we decide that it's Y right now, and we make that choice. And then we need to defend that choice. But if we can present an array and better use different possibilities showing to a model, then we can enlarge the way that we're communicating what we don't know at that stage specifically of the project. Because you can have A, you can have B, you can have C. Based on our geological judgment, we tend for A and B, but here is what it means if it's C. You know what I'm going with this? So it's just an additional tool to sort of provide better communication at all the stages of the different project stage. So that's kind of the opportunity that I'm seeing with AI tools for the modeling side of things.
Yeah, look, I agree with what everybody's saying here. And just to support Luca's comment, there have been up to 10, 15 years ago work done like that. Wellman and Kumar in 2018, they've created models that have a selection of potential positions for faults, for example, that and you can, and obviously there's a one particular representation would be a higher likelihood, and every second or third, fourth one you reduce in the potential position of those things. So people have been playing around that for some time now, and I don't necessarily think it's AI, but it could start to fall within that realm of AI.
So sorry, just while Wayne was talking, something just occurred to me that you could build an AI model or a series of AI models, but you'd have to reconcile them to the stresses that cause the fabrics and the discontinuities and the rotations in that model. And to me, that's the biggest trick, right? So you can create something with 3 or 4 options, but will those 3 or 4 options actually make sense if you try and resolve how that fault was formed based on the imposed stresses on the volume? And to me, that's the key to get it right. It's got to that key has got to fit that lock perfectly. So you've got to be able to back reconcile. It's almost like a back analysis really to the causative stresses. And then the larger areas, you're going to have the effects of far field stress and near field stress, and it can get really complicated. But to me, that's the key to getting this right. And I don't know how you do that.
No, not on that scale. No, not yet. I was just talking about the position of a single fault. But yeah, absolutely.
And yeah, to reach that point, you need a very strong and robust data set with kinematic and all of that, which 9 times out of 10 we don't have it. We're just playing with interval that says fault. Maybe some alpha angle, maybe some good ATV, but that's what we're dealing with most of the time, right? So that's where, AI could help. Let's say provide options, and then you go in and do the detailed work to go back and start to reconstruct everything and all the deformational history.
There was just one comment I wanted to make, which is this is in parallel with what everyone's talking about here. I think one of the things that it's worth just bearing in mind and grounding ourselves in a sense of reality about these tools right now is there are no off-the-shelf tools right now that will actually go and model a fault or will model a domain. There are some, I know there's something in development from a fairly major player in the software industry that looks at domain changes, and you would be able to think about those domain changes as a guide to where you might see a structure. But right now, there's nothing off the shelf that we can go and plug in that will go and actually make a fault plane for us, something that defines a boundary. So I just think that's an important thing to bear in mind before anybody starts scurrying off to go and try and find tools that will help them build faults.
Yeah, all really good points. I think for the sake of time, we'll move on. It's a really interesting discussion. I'll mention that machine learning and AI is a big part of our final section of the course. So we'll be having a webinar dedicated to that in a couple weeks. So stay tuned for that as well. But thank you all for that discussion. We've got a couple live questions here. Let's get to one from Jean-Luc. Which fault parameters should be used to classify faults for slope stability purposes? Thank you, Jean-Luc. Switching gears here for sure, but a really good question. Somebody would like to jump on this? Or I can assign somebody.
I mean,
I think
I
it's
just repeat myself.
yeah.
Yeah.
Pattern properties continuity. If we're talking about the fault parameters in terms of the infill parameters, there are ways to characterize the infill, the gouge. I think Reed-Miller 2001 or something is a paper that I would definitely refer to. But again, we're not just talking about the infill parameters of a fault system. We're looking at that pattern and understanding the continuity of the faults. I think that's how we get to understand and classify the faults and use them in stability analyses.
Wayne, I think in one of your presentations you discuss quote unquote painting these parameters onto the fault surfaces.
Yeah. Actually, a recent paper as well, where that's true. So you can take the properties that you measure, and again that could be infill, fault infill properties, and you can color those based on the strength parameters that you have. We've done that on some models, showing areas where the rock properties are weaker versus places where they're stronger. That's not that hard. You can apply that in Leapfrog nowadays using the estimation parameters that you have there. Yeah.
Great.
The first thing I always do is to make sure we know what kind of fault is, so classify it by its type. First thing you want to do is make sure it's not a rubble zone, fracture corridor, a fracture swarm, other things that get labeled fault when they're not. So start with sense of shear, kinematic indicators, and what type of fault is it? Normal, reverse, thrust, strike slip. Start with those very, very fundamentals, the undergraduate level, because a lot of folk don't write those down or even start with those, and then progressively go through the different either length, connectivity, fill, etc., after that. But first of all, you've got to know what the fault is, so you can connect the dots between drill holes or outcrops. Fundamental.
Great point.
I
Not
think
always
the
easy.
question- Yeah, because okay. The question was about parameters, but yeah, okay.
Yeah.
I was actually going to just make a comment earlier about fault parameters. Sorry, I know Luke has his hand up there. I don't know how to put my hand up actually.
Like this.
I think just to dive into, I was thinking like if like the actual details that you may be interested in collecting when you're mapping a deposit. Some of the options or ideas you could collect would be like a fault core zone width. If you're looking at brittle structures, understanding what the gouge and their brecciation is that's comprising that fault core zone and the width of it. And then additional to that, what is the actual damage zone around that structure? Another parameter I think could be beneficial is understanding the persistence of that structure, how far reaching it is. And then also sort of evaluating the importance of that structure for your fit for purpose model. So if it is going to be for geotechnical purposes, what is the location of this and the orientation of it relative to a bench or a slope as well? So I think just kind of the nitty gritty for some of the details of collecting in the pit. Those could be some of the options I'd look at for parameters.
Very good. Luca, you got your hand up there?
Yeah, it's just to add, the best way that I usually approach this, it's thinking about what our geotechnical colleagues are collecting when they're doing scanline, for example. A fault is pretty much nothing different than a big long discontinuity. So the parameters that you're collecting or you're considering for stability analysis for a joint is the same one that you're applying for a fault. The name changed a little bit. Instead of aperture, we're talking about damage zone or thickness. Infill is the same. One of the things that we tend to overlook a lot, which I think ties up with one of the questions that will be coming up, it's the roughness along the fault plane. Whether it's a roughness on the plane or it's the undulation on the plane at the larger scale, because that has a massive impact on your stability assessment. So that is one of the aspects in which we kind of tend to overlook several times, even when we do data collection in the field. Roughness sometimes does play a bigger role in the overall stability assessment. So it's yeah, I wanted just to add a little bit of the roughness as well.
James, I just wanted to add one other thing here, and this is, when you're talking about classifying faults, the word classify gets used in a lot of different places, and we've been talking about the classification of faults from the perspective of their fault properties. There is an extension of that as well, which is that we do also classify faults by the risk that they pose. And in that instance, there's very fundamental parameters that we haven't mentioned yet, which are dip and dip direction of a structure. And how that aspect, literally the orientation of a fault is, and the risk that it poses is going to change depending on the orientation relative to the pit. That'll, we'd usually define that using the geotechnical design domains. So it's just there is, although we're diving into water and infill and all of these things, let's not forget dip direction relative to the pit slope and which geotech design domain you're sitting in is still an important thing as well. So that classification of risk.
Yeah, very good point. Absolutely. All right. I think we'll move on to a somewhat related question here. Thank you, Jean-Luc, for the question. Very good. So this one is somewhat related to the previous question. I'm working on a structure model, and when I average a surface through our messy data points, I'm left with a smoother surface that my geotech says is less stable than the more complex surface created when I stick to each data point. They're telling me we should use the smoother surface because it's more conservative for design. Thoughts? And I've gone ahead and drawn this little schematic based on what I interpret to be the question, where you're averaging through the data points on the left, and then you're adhering to each data point on the right. And the suggestion is that the fault interpretation on the left would be less stable, perhaps because it's smoother. So interesting question.
Yeah, maybe James, I can jump into that.
Please
I
do.
actually really like this question. I think the most important thing that I would do here is try and figure out if you're looking at one continuous fault surface or if you're looking at a variety of connected faults or a fracture system, because you might be just measuring different data points along a network of faults that are not necessarily connected as one discontinuity surface. So again, that comes back to some of the fault parameters. Do all your data points have the same fault parameters, actually part of the same fault? Or, I mean, ideally pit wall mapping, getting some kind of exposure of this fault or fault system to determine that. So that's kind of the first part that I would try and figure out. And the second part would be looking at the confidence of each of your data points. And I guess I would also question like GPS accuracy, if your data points are kind of staggered like that, or yeah, is there anything else you can figure out around the data points? Are they all the same high quality data sets? Otherwise, I would probably snap your fault mesh to the highest confidence data points first, see if that creates a very smooth surface. If that's still staggered, then I would be looking at a few other things.
Very good points. Thank you, Neil. Anybody else?
You could be measuring splays in an anastomosing series of structures within a fault zone, for instance. So in that case, you know, what would you do? It's really, it is an interesting question. I don't think you necessarily want to sort of create a sort of step path thing. I don't think you'd want to do that. I would tend to lean towards the one on the left, but then I would also question if you are measuring the same structure all the way through, or if you're looking at splays, or maybe you've strayed into the damage zone or something like that. And again, are you know, should you be modeling this thing as a discrete line, or should it be a volume? That's another question, right?
Exactly. So following on from that, I personally would model it as a volume. You could use those data points as the envelope of the volume. A fault is rarely a surface, it's usually a part of a network of faults and fractures. Don't assume it's a single surface.
That's a great point. A lot of people, different loggers will choose either the top of the fault or the base of the fault when they're logging in the core, and you just don't know sometimes. That's a great point.
But
yeah, Neil.
I think still with the volume approach, you have to figure out the smoothness or continuity of that surface, right? Even if you have a volume-based model, you need to know how your fracture system within it or your faults are connected, in order to give that the right parameter, even as a volume.
Yeah, with the volume, it's very tricky sometimes because the assumption, you know, that ties up with what Ian was saying earlier about, you know, you leave a model to a client and then they come back 2 years after and then they assume, right? So the risk is that if it's not communicated properly, then that volume is considered to be a full gouge of like X amount of centimeter of meter, whereas in reality, you're just defining a zone that have some degrees of interconnectivity or some percentages of rock bridges that may actually not be an issue for stability wise, or can be a complete issue for the stability of the open pit. So even with the volume can get tricky if it's not communicated properly.
Yeah, again, I would steer clear of the one on the right, because you could introduce an artifact into a section where people think you've got this sort of stacked egg box effect where everything's holding up nicely in itself, when that's actually not the case. And I've seen lots of models in, you know, via Itasca where they tend to do this, and it's just not realistic. So yeah, I would tend to try and model a more continuous, smoother structure. You know, although maybe you've got refraction of your structure through rocks of various competencies, there's an option. You get that with joints, you know, and definitely with some faults. So it's not impossible, but just be careful about imparting this false sense of security in a sectional view on things.
What are the fracture patterns and fault patterns that you see in the outcrop around you? The one is
Great point.
one more consideration is who collected the data and why were they biased to those data points? Is it because of the availability of seeing outcrop versus soil, or was it, how much time did they have? And so we don't join the dots because the dots are biased by the human. So it's a zone of damage. So most faults are. Call it a shear zone, call it something like that, but it's not a surface and it's not joined dots.
Yeah. Great. Well, for the interest of time, I'm going to move on. We've got a live question that I think is somewhat related to this from Mustafa. How would you quantify and incorporate visually systematic rock bridges into your model for structurally controlled slope stability? Thank you, Mustafa. I think that's a very good question. So how would we go about quantifying these rock bridges if the structures are not connected, I assume?
Well, sorry, it may be semantics, but what does visually systematic mean? I don't quite understand what that means.
Yeah, good question. Maybe perhaps that you're observing them in the pit.
I think my interpretation of visually systematic is just what you're saying there, James. It's you're standing in the pit and you can see you've got 2 or 3 structures that are coming down with rock bridges and overlapping tips. And I've built out a number of these, and I've had a lot of discussions. I've actually stood in the pit with the geologists from site who are focused on the resource end, and their position was, well, we just model the whole thing through, all 3 of these as one single surface. And my answer was no, they are, these aren't offsetting the resource in any meaningful way. We can see there's rock bridges. We have to model in what we can see, because if there's a rock bridge, that's a much more positive scenario for the engineering design. So we model it realistically. So I think the short and I think pithy answer is model it the way you can see it. But I think the more complex part of that is that typically you're only going to be able to do that once there's actually good exposure. So it really emphasizes that importance of mapping and modeling as your mining progresses, because that level of detail, being able to see those rock bridges, you can't do it from drilling. Like it's not those 3 structures that are defined. We would probably just turn them into one based purely on the drill holes. So it really emphasizes, like, what this question emphasizes to me is the importance of mapping and constantly gathering that information about the structures as you're exposing them.
Yeah, sorry, Neil, do you go?
No, go. Okay. I was just going to add to that too. I think a note of caution too. If you're in the first couple of benches of your mine and you're seeing these rock bridges and depending, of course, how wide they are, but as your mine progresses and as you continue blasting the rock and excavating that rock mass, I think it's really important to just keep monitoring those, because there is potential that through continued blasting you might actually connect these, and then they causing more instability than they did at the first few benches. Of course, this is a scale thing. If your rock bridges are super far apart, then that might not happen.
Yeah, to me, there's a number of underlying practical issues, Mustafa. So, firstly, what data do you have, and at what scale are you trying to model? Most packages that we use to build these kind of models, or the ones that we use, use radial base function, RBF, or fast RBF if you're using micromine, and they don't like discontinuous surfaces that terminate in, like that, without terminating against something else. So there's a fundamental constraint on the tools that we use to represent these things. On the other hand, if you were to look at something on a much larger scale, the oily packages like GoCAD, they're very happy to accommodate blind faults, which might overlap and which may then make sort of bridges and that kind of thing. So, to some degree, your bridge is an artifact of modeling, you're not modeling the bridge per se. It's an artifact of the structures that you model. The question is, can you model discontinuous structures that end, or what are they terminating against? So for me, it's a very tricky thing to actually represent in the model, and I'd like to hear what the other panelists have to say about that, if they've managed to actually explicitly model these things. Do you put it on artificial block boundary? What do you do?
Yeah, very good. Luca, I see you got your hand up.
Yeah, one approach that we use, it's once you define the damage zone of a fault system, we use DFN. We use DFN approach, and you can actually do stochastically the representation of variability of the distribution on that one. One thing that I want to highlight, though, is that rock bridges is very much a stress term. What you consider to be a rock bridge, because you see two joints discontinuity or faults that overlap and not connect, like with a hard linkage, doesn't mean that it's going to break, or it could mean that it's breaking anyway, because it's very much a stress related problem with rock bridges. So you can have 100% of rock bridges, which means that your faults are not interacting, you're a small segment, but your slope is going to fail anyway. So we need always to put in mind, to put it in the back of our head, that if you have a lot of rock bridges, well, that becomes intact rock, and that it's a completely different story, right? So a percentage doesn't give you sort of like a peace of mind in terms of slope stability. But DFN is a way to go to quantify and have, or at least a stochastically distributed possibility of percentage of interconnection between discontinuities.
All right. Great discussion, everybody. And thank you, Mustafa, for the question. Really good question. Move on to one kind of on the same theme, actually. This is in reference to one of Wayne's presentations from the course. So in the module 1.2 presentation, there's an example of an unrealistic cross-cutting fault model, which I've clipped up here. It's the image on the left, and a real-world discontinuous fault zone, which is up here on the right. I come across the former all the time, and the justification is that there's a lack of evidence for deciding where faults terminate against other faults. I agree that they're unrealistic, but when a modeler does start terminating or offsetting structures without evidence, isn't that problematic also? And this is directed towards Wayne and Finley, so maybe I'll start with you two, and then we can open it up.
Yeah, let me just comment. Yeah, I love these two slides. I use them a lot, and it's really there to make sure that the modelers are really thinking about what they're doing and trying to be realistic in terms of what they're representing and providing to the geotechnical engineers. And it really comes down to an issue of reliability in terms of where this question is going. You may not have enough information, but you could. I'm presuming in most cases the person can go back to the field and can go look and see where what the cross-cutting relationships are. You may not need many examples to make examples of observations where you see clear cross-cutting relationships, and then you can start to apply that to the entire area. That at least will rapidly increase your reliability of your model. So I might have answered everything. Finley, do you want to add anything there?
Yeah,
So
look, I think this is a really interesting question, because it gets down to like what can we practically do, and I think what's wrapped up in this question but not explicitly stated is, why do we build models? If we go all the way to the end and we take, like at the end of the day, what we're doing is we're either defining domains or we are defining discontinuities that pose a threat to our pit design or underground stope design. If we don't have even an attempt to get a realistic continuity in there. If we have what, you know, the joking term is a pickup sticks model where all the faults keep going, the model is not able to perform either of those two functions. It cannot define domains because all the faults cross-cut, and it also really can't accurately define what the potential risk is because, again, the faults are projected all the way out. I think how you define what is actually realistic for those is going to be very, like, we can't give you a recipe book for that because it's going to come down to the data that's available for that particular project. So if you have mapping, that goes directly to what Wayne's saying. If you're working with only drilling, then yes, things get harder, but that's where typically we're still looking for other evidence about those patterns, but we'll usually go, rather than going from the drilling down to the smaller scale and looking at we'll go backwards and we'll work all the way up to the regional scale. We'll look at the geophysics and we'll look and find those patterns there and try and bring those patterns and that knowledge in. Maybe we'll do lineament analysis. The other thing that is important to think about, and this is a really tricky thing, but it's something that I think, you know, we have to kind of bear in mind, is we don't want to totally classify, you know, the potential continuity of faults by their damage zone. That's a very risky thing to do, but in the absence of any other proxy, if you have a big wide damage zone, it's more likely to be a more continuous fault than other ones. So if you're looking at a situation, and this is where I think, like, a lot of these pickup sticks models, if you started to actually classify, you know, bringing it back to that discussion of fault classification, if you started to classify some of these by the observed damage zone thickness, you know, the estimated true thickness and how that varied, and you actually classified the faults by where's the supporting evidence, I think you pretty much immediately start to take these pickup sticks models and be able to make some decisions. Yes, they're difficult decisions, but if we don't make them, ultimately these models are not fit for purpose for anybody.
Nice. Thanks, Benny.
Yeah, very good. Thank you. Thank you both. Any other thoughts on this? We're getting pretty low on time. There's a couple questions I'd like to get to. So for the interest of time, I think I'll move on. Here's a really interesting question. This is directed to Graham and Jeff, and then we'll open up to the panel. How do we communicate all the little decisions and assumptions that go into making a structure model? Our current model is taken as gospel, but once you realize how it was made, you understand all the uncertainty that's baked into it. So I'll kick it off with, let's get off with Graham and Jeff, and then we'll open it up.
All right, I'll go first. The first thing is that you must communicate as frequently as possible, let's say at least once a week. Have a decision register, have an assumptions register, and be able to talk with the stakeholders every week. This is what I'm assuming, and this is why. What do you think? Make sure it's an open two-way workshop rather than a one-way explanation. That's fundamental. The client or the person that's paying for this model ultimately is the decision maker about what to do next with it. So they have to be very involved in all of the communications and the decisions. I always have a decision register with every client. And I always say, we discussed this week. This is what we decided together based on the uncertainties. That's really, really important. The current model is taken as gospel. It shouldn't be, because it's just one 3D digital sketch based on only a very small amount of knowing the actual rock volume. Always write down what all your uncertainties are. And it's your uncertainty. Uncertainty is a state of mind. It's not the model's uncertainty. The model doesn't have uncertainty. You can't think. It's the human that has the uncertainty about some parameter in the model. So always list all the uncertainties, the biases, the likelihoods that you're proceeding in the right direction. You're choosing one of many possible outcomes because you haven't excavated that rock volume yet. So you have to be very clear why you're choosing this particular style, format, dip direction, connectivity, pattern over any other that could be there in nature. It's really, really important. So lots of communication as frequently as possible. I ask my clients probably once a week, and I have an end of week meeting every single week. And I just say, this is what I'm not sure about. What are you not sure about? How do we go forward with this on Monday morning? It's fundamental. Assume that most things you are putting into the model, into your sketch, a digital sketch, actually aren't that way in nature. So again, what's going to have a material impact and what isn't? And that's one of the uncertainties. So lots of discussion, frequently, two-way, open to listening, open to changing your opinion.
Excellent.
Yeah, if I'll add on, I know we're sort of pressed for time here, so I'll be quick here. But I really like Graham's points here, just constant communication. I think that's so powerful. And then I thought I could think of three things that we've done in the company to help sort of communicate confidence in structures. One of them is a memo at the end of the model describing each fault, sort of the data that went into it, the confidence of it, some of the questions you have associated with it. The second thing I can think of is some software programs allow you to actually create comments about the wireframe. You can link it directly to that wireframe. And so what I've seen in the past too is like, I'm modeling this in, but I have questions about this data set, about this orientation, this cross-cutting relationship. So I've seen that as an option. And then the third thing is, and there's a paper about it in the Slope Stability Conference back in Brazil, I think, or maybe it was in Arizona, but there's also heat maps, 3D confidence heat maps that you can develop and build in a very subjective perspective. So as the modeler, you understand the data, you understand the quality of that data, and you can develop 3D confidence heat maps for structures of the most important to relay where your confidence levels are the highest and where they're the lowest, so that other stakeholders can look at and realize, okay, is this actually this data gap area, is it an area of concern or not? All right, that's my quick 2 cents on that.
Yeah, fantastic points.
Can I add one very small point to that too? I think we often communicate confidence in the model at the beginning when we hand over the model to the geotechnical engineers. I think we should also have a second step where the geotechnical engineer takes the structural model, does a slope stability analysis. I think after the fact, it would be great to have another meeting where the geotechnical engineer tells you what assumptions they have made in their model and what their thought processes were and how they have evaluated your structural model. Because often I find it's that afterwards, that meeting, that communication where you're like, well, no, actually, that's not how I would have interpreted, or you can, communicate again.
Yeah,
Building
Neil,
on what Neil's saying there about a look back analysis, which the purpose of that is to then iterate. One model information comes available, then iterate it again. You want to know what piece you're iterating, what had the widest uncertainty, and are you now narrowing that uncertainty? The purpose of collecting data is to narrow uncertainties, so make sure that that's happening rather than adding more ambiguity.
I just wanted to really support what Neil was saying there. The ensuring that the model is used the way that you intended it to be used is a very key thing. You'll find, the larger your team, and larger doesn't have to be very many people for communication to kind of stop and for assumptions to start being made. But something you will see that's quite common is if you classify faults into high, medium, and low confidence, which are very sort of broad subjective buckets as it is, I've seen multiple instances where engineers will say, I'm taking out all of the low faults from the model, all the low confidence structures. And they're not low confidence that they're there, they're low confidence in their orientation and properties. But if the engineer doesn't understand that, or they're coming into that project with assumptions from a prior structural geologist they worked with, down that path lies disaster. So Neil's point is incredibly important, making sure that they're to ensure that your model is being used the way that you intended it to be used.
That's very, very good points, everybody. I don't want to cut off this excellent conversation, but in interest of time, we probably need to wrap things up here. So I just want to once more mention that this webinar is based on our Structural Geology for Geotechnical Professionals course. If you'd like to learn more, you can follow the QR code, or you can, I think there's a link in the chat to this course and our other courses as well. And with that, I will wrap things up and just say thank you again so much to our panelists and our participants. It was a really good conversation. Very much appreciate it.